Hi, I'm Mike Louie. Welcome to a room that I'm in. I'll be presenting Understanding Capacity Driven Scale Out Neural Recommendation Inference. I'm aware that's quite a mouthful, so to put it a bit simpler, we'll just be discussing how distributed computing is applied to a unique class of neural networks. This work is a collaboration between Facebook, Drexel University, and Tufts University. My co-authors are Yavuz Yedem Oz Ashkin, Zuran Zhao, Xinye Sai, Carol Jean Wu, and Mark Hempstead. This work would not be possible without countless others, whose names I cannot fit all on one slide here. There will be two broad parts to this talk. First, I want to introduce and motivate distributed inference as a significant system and workload. This is arguably the most important part of the talk. We want to provide the community more insight into this unique workload. Second, we want to provide a baseline set of measurements, analyses, and knobs to see how feasible it is in the data center. So, part one. To begin, I'll introduce what a recommender system actually does. So, a recommender system suggests or ranks items from a particular set for a given audience. In this case, our audience is our user. To do this, other inputs are used in the system, such as preferences of similar users, a user's history and their own preferences, and environmental features, for example, the time of day or the current location. Examples of recommendation include search results, question and answer systems, scheduling, books, in this case, music, movies. So we can already see that any impact we have will have a widespread effect on many domains. There are many methods to achieve a good recommender system, and this talk specifically focuses on a relatively recent recommender system that uses deep neural networks. Hence, these are neural recommendation systems. So we now know that this is an important application. It's an important workload. Let's put that into context of designing a system and infrastructure for it. There's conventionally two design constraints for these models that I'm going to cover right now. Later on in this talk, I'll discuss a third constraint that we identify as new to this specific work. So the first constraint is latency. If the model is fast and produces an inference result quickly, the user is happy. They aren't stuck staring at a blank page or waiting for their results. This is actually the most important constraint because if the model takes too long to produce an inference, a less accurate fallback model is used that provides not as good of a result. For this reason, tail latency is a paramount metric for a recommender system. The second constraint is simply the scale of compute. Neural recommendation has been cited as using up to about 80% of all inference cycles in Facebook's data center. Facebook uses AI to enhance many of their services, so we can see that recommendation inference is a significant workload. The infrastructure must be able to scale to millions and billions of users that rely on the models, as well as remain within tolerable bounds to constrain energy consumption. Lastly, I just want to differentiate inference from training. Performing inference and training a model are closely linked, but their system-level goals are different. Compared to inference, training is more concerned with a single system consuming large amounts of data to generate an accurate model. The different system considerations are emphasized when discussing distributed training versus distributed inference. Now that we know more about neural recommendation, we can begin to look at the details of its design. So you're probably familiar with the figure in the middle here of a dense neural network. There is a vector of continuous inputs, so an array of floats that is input to a series of matrix multiplications and activation functions. Recommendation models diverge from traditional dense neural networks with the addition of categorical features. So categorical features are things like a user's last listened to song or their favorite album. They aren't directly usable by neural networks. Instead, each feature is hashed to one or more indices shown at the bottom. And those indices are then looked up into a table. The values are then combined in what's called a pooling operation, which is normally just a simple summation or a concatenation of those values. These tables are called embedding tables, and their values are learned during training. Embedding tables are sparse and they are large. They're considered sparse because only a fraction of their values are accessed for each inference, and they're large to reduce the number of collisions that happen between different feature inputs. However, their size still ends up being constrained in order to fit on a single server node. After the embedding table lookups, a series of dense layers combine all the intermediate results and produce a final. So this is the general architecture. However, variations do exist. That finally brings us to our third constraint, the newly introduced constraint for this work, and that is model capacity. The trend over the last 3 years has been increasing model size, an order of magnitude increase in just over 3 years. So what's causing this trend? Well, as we increase the size of the embedding tables, there are less collisions, as we said, and therefore increasing table size is a straightforward way to improve the accuracy of these models. Additionally, we're seeing a similar increase in the number and variety of sparse features used as inputs to these models as well. So for all intents and purposes, the growth in model size can be entirely attributed to the embedding tables. This presents us with models on the scale of hundreds of gigabytes to tens of terabytes in size, especially for the billions of users worth of inference. Currently, traditional web servers cannot support models of this scale. And for a number of reasons, recommendation is usually served on CPU. There are some ways we can quickly support these huge models. For example, we could increase the amount of DRAM on a machine. Another option is to page in embedding table data from fast storage. Both these solutions require additional hardware support and to some degree also require additional software support. That brings us to splitting the model across multiple nodes and serving the model in a distributed manner. We were interested in a solution that could be easily deployed quickly, so this is what we settled on. It's a low-risk, scalable solution that does not require additional hardware support. Each of these solutions, as well as others, have their trade-offs, but as an initial first step, distributed inference was the most practical. This workload is an opportunity for system researchers to collaborate with machine learning architects, and the solution space is still quite young. In this slide, I'll briefly touch on the changes we made to the model architecture to enable distributed inference. Recall the conventional way recommendation is served is on a single server node on the CPU. The increasing size of the embedding tables makes this solution non-viable as the models grow and grow and grow. So what we do as a heuristic is to move the lookup and pooling operators to their own neural network. This accomplishes our goal of spreading the memory capacity requirements across multiple nodes. Remote procedure call, or RPC operators, are put in their place as a virtual embedding table. There is more detail in the paper if you are interested. I'll additionally walk through an inference request here to give a more concrete view on the implementation and point to sources of latency and compute overheads, which I earlier touched on as being critical to recommender systems. Remember, the challenge we have is balancing these three constraints of latency, compute, and capacity here. So in this case, we have 3 shards in this example, and each one runs a full inference service. Now, a shard is just a term for a service that's been split or sharded into multiple pieces. So 3 shards here. We didn't place any of the embedding tables on the main shards for our experiments, but that's certainly possible if an embedding table is small and frequently accessed. So here the main shard executes all the dense operators. You can see here FC stands for fully connected. and issues the new request to the remote shards in parallel. The remote shards, which can have multiple embedding tables, perform the lookups and send the results back. The way the tables and operators are sharded across nodes, so the way the tables are mapped and split up, does impact latency and compute, which we'll touch on a little bit later on. The additional latency is largely attributed to the network link, while the additional overhead, compute overhead, is largely attributed to the act of just running another service. The actual impact of each is dependent on the specific model being served and how the model is distributed. Also, note that the requests are sent in parallel, so there is the potential of speed up here. However, in practice, we found this is difficult to achieve. These overheads are directly attributable to the choice to make each shard its own independent service. So this makes the system more flexible, but at the cost of some performance. With that introduction, we can begin to evaluate the system on representative workloads within real infrastructure. So that brings us to part 2. In the interest of time, I'm only going to discuss a few interesting takeaways from our evaluation. I'll be discussing the broad strokes of how the models are affected by distributed inference, and reciprocally, how distributed inference is affected by the models. There's far more discussion in the paper, so please check it out if you are interested. Our evaluation largely focused on the interaction between different model implementations and different table mapping or sharding strategies. For the following discussions, I'll be focusing on our naive sharding strategy of moving tables to ensure each shard has equal memory requirements. However, other sharding strategies, including balancing the number and amount of compute per node, were also investigated, which is in the paper. So we ran 3 representative models with 3 different distributed sharding methodologies. Here we see the overheads for DRM1, which was our most compute-intensive model. DRM1 simply means Distributed Recommendation Model 1. Mentioned in the prior slide, we showed just one sharding methodology in the interest of time, which is the capacity-balanced strategy. The graph on the left shows end-to-end latency overheads across each configuration, and the graph on the right shows compute overheads. We see a clear trend of latency versus compute trade-off as we increase the number of shards. This is expected. By doing so, by increasing the number of shards, we increase parallelization, but we also increase the number of full inference service requests. Recall that tail latency is what we really care about. So as far as that's concerned, here in the 99th percentile, that's tail latency. As far as that's concerned, we see very acceptable overheads. Arguably, average or median, 50th percentile, the average compute overheads is more important than tail compute overheads, since it can translate to additional servers to handle load. In that case, there are certainly improvements to be made to optimize the software infrastructure. So let's dig into why tail latency works out in our favor. This graph shows a breakdown of the 50th percentile end-to-end latency. Again, as we go left to right, we are increasing the number of shards. The layers from top to bottom are dense operators, the embedded portion, and then the various serialization and service-related software layers. The embedded portion constitutes just the sparse operators, so the embedding, lookup, and the pooling operators for the non-distributed model. So singular is when it's not distributed at all. So this is just the lookup operators. In the distributed models, the embedded portion represents the longest critical section asynchronous lookup that's performed. So it's no surprise that the only part that changes as we increase the number of shards is the embedded portion of latency, which decreases as more work is parallelized. When analyzing the tail latency measurement, so now we're here in P99 tail latency for the same end-to-end breakdown, we see that much more of the time is spent deserializing the large requests. And those large requests are what's producing the tail latency. In turn, substantially more of that latency is also spent computing the dense layers, which constitute more work than the sparse layers. So simply put, there is less impact from distributed inference when we're looking at these tail latency scenarios. This helps guide us to where we want to focus efforts to improving latency and supporting new models. We can also zoom into that embedded portion to see how the various layers within it affect a remote lookup. So in this graph, we've zoomed into that embedded portion of latency to see how sharding is affecting it. Again, in the non-distributed version, the latency purely is just coming from the sparse lookup operators themselves. In the distributed versions, the latency overhead comes from the network link, additional serialization overheads, and the remote service itself. Clearly, in the one shard configuration, we're only incurring overheads since none of the work is being parallelized. As we parallelize more work, latency is reduced. However, the network link is still dominating. At the same time, we also see that a large portion of latency is consumed by the supporting software infrastructure. So this characterization is an important step toward improving distributed inference to support models that cannot tolerate increased end-to-end latency or don't have sufficient work to parallelize. For example, all the data shown so far is for DRM1, which has a long tail of embedding table sizes shown in the graph to the left. So this is the number of embedding tables and their size for each of our 3 models. DRM1 is in the red here. You can see its long tail. In comparison, DRM3, which is in purple, has far less embedding tables, and it's dominated by one huge embedding table to add to that. Furthermore, the proportion of its compute in DRM3 is far less than DRM1 when looking at the sparse operator compute. So, not only is there, less work to parallelize, but the work itself within those tables is also less. We can see the effect that this has in that embedded portion latency breakdown for DRM3 in this graph. There's simply not enough work to parallelize, nor could it be effectively parallelized because most of the work is a few lookups happening in that one large table, and that one large table is what's being distributed. Thus, it's also important to consider variations between models and to collaborate with machine learning architects when designing such systems. That brings us to the end of our mini dive into our findings. There's a lot more detail and data in our paper if you'd like to see a broader and more in-depth analysis. So future improvements to distributed inference include optimizations to the software infrastructure clearly and table placement, as well as co-design with model architects. Additionally, custom system architecture for these models, which were not discussed in this work, are also an exciting opportunity. In conclusion, we've introduced neural recommendation as a critical data center workload and introduced new challenges facing system engineers to scale that workload. The models are constantly evolving, so there's a need for system architects and machine learning architects to collaborate to meet accuracy, performance, and energy requirements. The design space is still relatively young, and there is great opportunity to further improve system-level solutions. Thank you for listening. Hopefully you found this talk informative and interesting. If you want to know more, you can contact me at my Drexel email. That's michaeldlouis@drexel.edu. And thank you.